All right, let's get right into it. We're going to talk about a really fascinating mechanism that solves a huge problem for high-speed blockchain networks. And get this, it's a brilliant piece of engineering that basically rethinks one of the most fundamental things we deal with every day, time itself. Now, this isn't some kind of sci-fi thought experiment, you know? It's a very real, nuts and bolts engineering challenge that super high-performance systems like the Casper network absolutely have to solve. I mean, think about it. When you're cranking out hundreds, maybe even thousands of transactions every single second, how on earth do you make sure everyone on the network agrees on what time it is? It's a huge deal. So before we jump into the solution, let's just take a second and really dig into the problem itself. We have to understand why validating time correctly is so essential for the security and really the basic integrity of any blockchain. Right, so here's the bottom line. Without accurate time, the whole system becomes incredibly vulnerable. You could have malicious actors just lying about when a block was created, and that could potentially mess up the entire network, screw with the mining difficulty, and totally undermine the trust that the whole system is built on. Okay, so let's see what happens when a network starts operating at an unbelievably high block rate. This is the exact point where the old solutions, the ones that worked perfectly fine for slower blockchains, just completely break down. So what's really cool here is the contrast, right? For a traditional, slower network, figuring out the median time from, say, the last 100 blocks, that's pretty straightforward, no biggie. But on a high-speed network like Kaspa, that same time window could have thousands of blocks in it. And trying to calculate a median from that massive set for every single new block, well, that becomes a massive computational bottleneck. It's slow, it's clunky, and it just flat out can't keep up. This whole situation created three very specific, very big problems. First, you've got that risk of timestamp manipulation we just talked about. Second, there's this thing called configuration inconsistency, which means the rules would act differently depending on how fast the network was going. And third, those performance bottlenecks we mentioned, which could just grind the whole system to a halt. It was obvious that a totally new way of thinking was needed. So faced with all these challenges, the developers behind Kaspa didn't just tweak the old method, they invented a brand new one. And it's a really elegant solution called past median time, or PMT for short. And this really nails the core concept. Instead of trying to look at every single one of those thousands of recent blocks, the system just takes a smart sample. It creates a much smaller, but still representative window of past blocks to figure out a valid time. This is the real breakthrough. This sampled window is always a fixed size, so it doesn't matter if the network is running at 1 block per second or 100 blocks per second, the amount of work needed to calculate the time stays exactly the same. This is what guarantees consistent, predictable behavior and just supercharges performance, no matter the network configuration. So this idea of a sampled window sounds fantastic, but how does it actually get built and how is it used? Let's pop the hood and take a look at the actual mechanics of this whole process. Okay, so the system follows this really methodical four-step process. It kicks off from a parent block and then works its way backwards through the chain's history. But, and this is the clever part, instead of grabbing every single block, it just samples them at regular intervals. It uses something called the DAA score to do this, which is basically just a measure of mining difficulty. It keeps collecting these really significant blocks until its little window is full, and then it stops. It's such a smart way to get a good snapshot of history without all that crazy computational cost. Now, here's another subtle but really important distinction. The algorithm doesn't find the true mathematical median of all the timestamps in its sample. Instead, what it does is it averages a small group of the values from the very center of the sorted list. This gives you a much smoother, more stable result that isn't easily thrown off by a few odd blocks. So for example, if you look at this sorted list of timestamps, instead of just plucking out the single value in the middle, the algorithm might grab, say, the 3 or 5 central values and average them together. This gives a much more reliable and representative timestamp for the network to work with. So, this carefully calculated time is then used in two absolutely critical network functions. First up is header validation. Any new block that shows up with a timestamp that's less than or equal to this past median time gets rejected immediately. No ifs, ands, or buts. And second, it's used to calculate the virtual state, which is kind of the network's agreed upon current state, making sure the entire blockchain is always anchored to a valid and secure point in time. Look, I know this might all seem a little technical, but the benefits you get from this system are so concrete, so powerful, and just absolutely vital for keeping the network healthy and secure. First and foremost, you get consistent security. This sampled window approach gives you the exact same security guarantees no matter how fast the network is blazing along. The rules don't bend, the protection doesn't weaken, and that is exactly what you want in a decentralized system. Secondly, you get optimized performance. By keeping that window to a fixed size instead of a list that could be thousands of blocks long, the system just slashes the amount of computational work it has to do. This dodges those performance bottlenecks and lets the network keep up its incredible speed. And maybe most importantly, this strict validation method is a brick wall against attackers trying to manipulate timestamps. They just can't submit blocks with times way in the past to try and cheat the difficulty adjustment or mess with the network's sync. The system simply won't let them. It's a closed door. At the end of the day, these kinds of innovative solutions like past median time really show us that even the core concepts we take for granted can be totally rethought and re-engineered to build faster, more secure, and way more scalable decentralized systems. It really makes you wonder, what other fundamental building blocks are just waiting out there for their own brilliant redesign?